Hey everyone, and welcome. Today we're diving into a pretty interesting Leetcode problem called set matrix zeros. It's a medium level one, and it's got a neat trick to solve it efficiently. We'll break it down step by step, so don't worry if it seems tricky at first. Let's get started. So here's the deal. We're given a matrix, which is just a grid of numbers, say with rows and columns. The rule is, if we find any element in this grid that's a zero, we have to change its entire row and its entire column to all zeros. And here's the catch. We need to do this in place. That means we should try to modify the original matrix directly, without using a ton of extra memory for a copy. Let's look at the first example. We have a 3x3 matrix. The first row is 1, 1, 1. The second row is 1, 0, 1. And the third row is 1, 1, 1. See that 0 in the middle? That's at row index 1, column index 1. Because of that 0, its entire row, the second row, needs to become all zeros. So, 1, 0, 1 becomes 0, 0, 0. And its entire column, the second column, also needs to become all zeros. So the column 1, 0, 1 becomes 0, 0, 0. Putting it together, the final matrix looks like, first row is 1, 0, 1, second row is 0, 0, 0, 0, and third row is 1, 0, 1. Make sense? Here's another one. The input is a 3x4 matrix. First row, 0, 1, 2, 0. Second row, 3, 4, 5, 2. Third row, 1, 3, 1, 5. Okay, we have two zeros in the first row, one at the very beginning, row 0, column 0, and another at row 0, column 3. The 0 at the start means the entire first row becomes zeros, and the entire first column becomes zeros. The 0 at the end of the first row means, again, the first row becomes zeros, which it already is from the first 0, and the very last column, column 3, becomes all zeros. So the first row is all zeros, the first column is all zeros, and the last column is all zeros. The numbers in the middle that weren't in these zeroed out rows or columns stay as they are. Alright, so what's the first idea that pops into your head? Maybe we could scan through the matrix, and as soon as we find a 0, we just stop and change its entire row and column to zeros, right? Well, there's a slight problem there. If we change, say, A to a PUC A as part of this process, that new 0 might then incorrectly cause its row and column to be zeroed out, even if it wasn't an original 0. That's not what we want. Okay, how about this? We first go through the whole matrix and just make a list of all the spots that have an original 0. Then, once we have that list, we go through it and zero out the rows and columns. That would work, but it uses extra memory to store those locations. The problem asks us to do it in place, ideally with very little extra memory, so we need something a bit more clever. So for a solution, often meaning constant extra space or big O of 1 space, we need a trick. What if we could use parts of the matrix itself to keep track of which rows and columns need to be zeroed? Here's the core idea. We can use the very first row and the very first column of the matrix as our zero. Think of it like this. If we find a 0 at some position, let's say row and column, and this position is not in the first row or first column, we can signal that row needs to be zeroed by putting a 0 at the start of that row, that is, at row column 0. And we can signal that column needs to be zeroed by putting a 0 at the top of that column, that is, at row 0 column. But wait, what if the first row or first column themselves originally contained zeros? If we just start overwriting them as markers, we'll lose that original information. So before we do anything else, we need to check if the actual first row has any zeros, and if the actual first column has any zeros. We'll store this information in two simple true/false flags. Let's call them first row has 0, and first column has 0. Okay, so here's the plan, broken down. First, we'll figure out if the original first row needs to be zeroed, and if the original first column needs to be zeroed. We'll save these two facts using our quote, first row has 0, and first column has 0 flags. Second, we'll go through the rest of the matrix, everything except the first row and first column. If we find a 0 at any spot, say row column, we'll put a 0 at the beginning of its row, that's row column 0, and a 0 at the top of its column, that's row 0 column. These are our markers. Third, we'll go through the rest of the matrix again. This time, for each spot we'll look at its marker in the first column, and its marker in the first row. If either of those markers is 0, it means this spot needs to be zeroed out, so we set it to 0. Fourth, we'll use our first row has 0 flag. If it's true, we make the entire first row all zeros. And fifth, we do the same for the first column has 0 flag. If true, make the entire first column all zeros. This way, we use the first row/column for marking, but handle their original state correctly. Alright, here's the Python code for this smarter approach. I know, it looks like a bit of code, but don't worry. We'll walk through the key parts one by one, in plain English, so it all makes sense. Okay, first up, we get the number of rows and columns in our matrix. Then, we create those two important flags we talked about. First row has 0, and first column has 0. We start them both off as false. Next, we loop through all the cells in the very first row. If we find any 0 there, we set our first row has 0 flag to true, and we can stop checking that row. Then, we do a similar thing for the very first column. We loop down through all its cells. If we spot a 0, we set the, quote, first column has 0 flag to true and stop. So now, we know whether the first row or first column originally needed to be zeroed out, before we start using them as markers. Now for the marking part. We loop through the matrix, but this time we skip the first row and first column. So our row counter, let's call it starts from 1, and our column counter also starts from 1. Inside this loop, we look at the current cell, the one at row and column. If this cell contains a 0, it means we need to remember to zero out this whole row and this whole column later. To remember this, we put a 0 into the first cell of row, that's at row column 0. And we put a 0 into the first cell of column, that's at row 0, column. These are our markers. After we've gone through and placed all our markers, it's time to do the actual zeroing for the main body of the matrix. Again, we loop through the matrix, skipping the first row and first column, so starts from 1 starts from 1. For each cell at row column, we look at two places. First, we look at the marker in its row, which is the cell at row column 0. Second, we look at the marker in its column, which is the cell at row 0 column. If either of these markers is a 0, it means our current cell at row column needs to become a 0. So we set it to 0. Finally, we take care of the very first row and very first column, using those flags we saved at the beginning. If our first row has 0 flag is true, it means the original first row had a 0 in it. So we loop through every cell in the first row and set it to 0. And similarly, if our first column has 0 flag is true, we loop through every cell in the first column and set it to 0, and that's it. The matrix is now correctly updated in place. So how efficient is this method? Let's talk about time and space. For time complexity, if our matrix has rows and columns, we're essentially passing over the matrix elements a few times. Once to check the first row/column, once to mark, once to zero out the body, and then to zero out the first row/column if needed. Each pass looks at roughly times elements, so the total time is proportional to times. We call this big O of m times n, or order mn time. And for space? Well, we use those two boolean flags, first row has 0, and first column has 0. That's just a tiny, constant amount of extra memory, no matter how big the matrix is. So the space complexity is big O of 1, or order 1, which means constant space. That's excellent, and it meets the in-place requirement perfectly. So let's quickly recap. The main challenge in this set matrix zeros problem was the requirement, meaning we couldn't just make a new matrix or use lots of extra storage. The clever solution involves using the matrix's own first row and first column as a kind of scratch pad or set of markers to remember which rows and columns need to be zeroed out. The crucial part is to first save the original state of whether the first row and first column themselves needed zeroing, before we start overwriting them with markers. We did this with a couple of simple boolean flags. This approach lets us solve it efficiently in order m times n time, and, importantly, order 1 extra space. Hope that breakdown made sense and helped you understand the set matrix zeros problem a bit better. If it did, feel free to hit that like button, maybe subscribe for more Leetcode explanations, or drop a comment if you have any questions or other ways to solve it. And hey, if you're feeling super generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.